tests for chi-square. The first one was a goodness of fit test. So when you are doing a goodness of fit test, it is one population for one categorical variable. So think of M&M colors. There's a claim from the company that makes M&Ms that 30% are red, 20% are green, whatever. And you go out, you buy a bag of M&Ms, and you're trying to see, does my sample fit what the population distribution is supposed to be? If it fits, great. If it doesn't, that's when we have the alternative and we reject the null. So what you'll find on the review that you got today, the first page of it, all of it is kind of like a summary of the difference between the three tests. So for chi-square goodness of fit, it is a one population, one categorical variable. Typically when you see this question, it's like a single table, one row or one column, and it has typically expected values for that particular group. When you go into homogeneity, that is when you're trying to look at populations and see, are they the same or are they different? Usually, if you see this word with a two-way table, that is going to be your indicator. This is a test for homogeneity. This is going to be for 2+ population, so 2 or more, and it's still going to be across one categorical variable. So if I'm interested in different grade levels, freshmen, sophomores, juniors, seniors, and I go out and I sample 50 freshmen, 50 sophomores, 50 juniors, 50 seniors, that is checking my box for 2+ populations. And then I go in and I ask them, well, what kind of pets do you have? And then we get like dogs, cats, fish, things like that. And I try to see, is the distribution the same or is it different across the different grade levels? So if I think it's 40% dogs, 60% cats, is that the same distribution for each freshman, sophomore, junior, senior? The big thing to notice here, and I try to point this out again just because sometimes the wording of these questions gets a little weird and you're like, which one am I doing? This is going to sample separately. And so by that, I mean within the question, it's going to say, I sampled 50 freshmen, 50 sophomores, 50 juniors, 50 seniors, and it will indicate that they were separate samples. When you go into a test of independence, which is the new one today, this is going to be a test where we are going to see, kind of based on the name, is it independent or is it not? And this is another thing where if you see these words, that is your big indicator, I'm doing a test of independence. This is going to be one population, but it's going to have 2 categorical variables. And a lot of people get these two mixed up because sometimes the categorical variable that they ask is going to be something that in our heads, we think is separating them into different populations. So say, for instance, we take one big sample of 100 high school students, and then I ask them, what kind of pets do you have, or what's the pets in your household? And then I ask them, are you a male or a female? A lot of people will take male and female as different populations, which true, yes, it could be. But it all depends on how you sample. If you take a single sample, and it will be in the question, they sampled 100 high school students, it is going to have to be a test of independence if you are looking at 2 different categorical variables. Don't just take the fact that it is separating into different populations in our head as it being a homogeneity. The big indicator for you at the end of the day, like the first thing you should be looking for is, do you see these words? Because that's going to be the big difference between the two. But if you still just can't figure out after you've read the whole question which is which, look at, did they sample separately or did they take a single sample? Sampling separately is going to be your homogeneity. Single sample is going to be your independence. And everything else about these 2 tests, at least, the goodness of fit is kind of its own category. Everything about these 2 is identical, other than the null and the alternative. So just to kind of highlight what the null and the alternative are for this particular test today, null is going to be that they are not associated. Alternative is going to be that they are associated. Remember, the null is always the dull. So it would not be very interesting to us if there was no relationship between these two variables, which is why that is the given claim. Typically, you get to choose whether you want to use the word independent or associated. I tend to favor associated because it makes a little more sense whenever you're kind of trying to relate the two variables to each other. If you like independent and you want to use independent because that's the name of the test, you can. I just find that more people write them correctly with the associated word. It's something about it being a not for the null and an associated for the alternative, but usually that works out for people. So it's up to you. In my examples today, I'll use the word associated, but you can also interchange those with independent. Just remember that independent is equal to not associated. They don't have a relationship with each other. That's where people get confused. 3 conditions. Again, everything today is identical to what we did in 8.2, which was like a week and a half ago. We have a random condition. We have a 10% condition. Those 2 things, remember, you are always doing these, no matter what. Does not matter what test you are doing. It could be a 1 sample t-test or a 2 proportion z-interval. You are still checking, was it selected randomly? Is it a 10% condition? The only time these change is if you are doing an experiment, which is what the little note says. And in those cases, we are randomly assigning the treatments, and we're, for the most part, assuming independence among the subjects. But those 2 things, always true. The check for our large counts is the last one, and it is the one that's different kind of across the board for all of our tests. But I'm going to go in and make sure all of my expected counts are at least 5. And this is something where we are going to get this info from the calculator. For a test of goodness of fit, we find those ourselves. We take the expected proportion, we multiply it by the sample size, and we see what we think it should be. In the case of homogeneity and independence, I do not recommend doing that. There is a longer formula, which is at the very bottom of your page, that you have to use in order to check or find the expected values. And even if you go through the trouble of finding them all by hand and you put them into your calculator and you run the test, your calculator is still going to override anything that you type in it for expected values. So you might as well just use the values that they give you. The name is, again, one of the 2 things that is changing, and it's a test for independence. You do have to indicate what chi-square test you are doing. They do not rely solely on the null and the alternative. This is one where you do have to say it's a test for independence or goodness of fit or homogeneity. This is the chi-square test statistic. This is going to be like your cutoff value for your p-value. This is on the formula chart. You don't have to memorize this, just as a note on formula chart. The part where you're doing the observed minus expected squared, that is your component. And so every single cell in your 2-way table technically is going to have this formula performed on that observed count versus the expected. And then at the end, you take all of those calculations, you add them together, and that's what makes your chi-squared value. This is just like a z-score or a t-score from z-tests and t-tests. It is the cutoff value on your distribution. This is not something you will, again, have to find by hand. You're probably going to use your calculator, especially for independence and homogeneity. I go calculator the entire time, just because finding all of these individual counts is too time consuming. It would not be my recommendation. To get the expected values, there is a formula that you have to use: row total times column total over table total. But again, this is probably not going to be what you have to do by yourself. This is going to be something that you're going to put the data in the calculator, run the test in your calculator, get your values back out. But sometimes there are situations where they'll ask you for an expected count. I still, even if it's a single cell, if you don't want to have to worry about doing that particular formula, you can just go in, run the tests, get all of the expected values, and find the one you need. That's probably your best approach, just because, again, it could be too time-consuming, not worth it at the end of the day. Once you get your chi-squared value, just a reminder, because a lot of us, not all of us, I was going to say all, will forget that you can get a test statistic. They give you questions where they're like, the test statistic is 20. What is the p-value? And then we blank, because you cannot put a test statistic into stat tests. In the case of chi-squared, you do have to use chi-squared CDF. If it was a z-score, you're using normal CDF. If it was a t, you're using t-CDF. So it really just depends on what your test statistic is. But in the case of chi-squared, it is always skewed to the right, and you are always shading to the right, no matter what. Always, all the time, forever. Chi-squared is your lower bound, infinity is your upper bound, every single time. You get your p-value. We'll talk about degree of freedom within the question, because I am going to show where it comes from, but it is specific for homogeneity and independence, exactly the same. The only change for degree of freedom, and I'll just write it here since it's been a long time, degree of freedom for goodness of fit is your number of categories minus 1. So it is kind of like doing number of rows minus 1 times number of columns minus 1, but in the case of goodness of fit, you're only going to have a one-way table, so it's kind of eliminating the other possibility. You run the test in your calculator. This does require that we use a matrix, and this is going to be in Stat Test C. This is one of the easier tests to run because you really don't have to make any decisions. You're not deciding what is my null value, is it less, is it greater, is it not equal to. You're putting your data in the calculator and you're running the test. That is all you have to do for homogeneity and independence. If the p-value is low, you reject the hoe. Same thing we've been doing. If you are rejecting, you have enough evidence to go against their claim. There is convincing evidence for the alternative hypothesis. So that is how we will interpret. This is literally the same sentence we've been writing since January. Everything from like getting your p-value to the end is the same. So let's go in and let's talk a little bit about specific wording for independence. Just because there is an association, you cannot establish causation. So it's kind of like correlation is not causation. The only time you can establish cause and effect is if you absolutely know for sure 100% that there is nothing else going on that is contributing to this relationship. And you cannot really figure that out just from an observational study. So one of the things that a lot of people want to do that you cannot do is you cannot say that one depends on the other. I know we have they are independent and not independent. You cannot switch out not independent with the word dependent because we don't know if it's X is depending on Y. Now, the reason for that could be that there is some type of outside factor, a lurking variable. We had an example way back in Unit 2 where it was like ice cream sales in New York and the murder rate in New York. Both of them were increasing at the same rate. It looked like there was a linear relationship, but there was an outside factor, the weather, the heat, summer, that was causing both of those numbers to rise and make it look like there was a relationship between the two things. So you cannot establish cause and effect. They will ask you questions saying, can we say gender causes what type of animal you have? If you don't have a controlled environment, and usually that's like a well-designed experiment, you cannot say that. So just because we decide there's no association, we cannot go in and say that they are or we decide there is an association, we cannot say that they are causing each other just because of how you collect your data. Okay, let's go in, let's do one together, and then we'll try one on our own. We have, Andrew thinks there might be a relationship between angry students and GPA. So he asks, do students who are prone to sudden bursts of anger have lower GPAs? And he took an SRS of 300 RHS students. He had each student take the Spielberger Trait Anger Scale test, which measures how prone a person is to sudden anger. And at the end of the school year, he calculated or collected student GPAs. Does the data provide convincing evidence of an association between anger level and GPAs? So the first thing you should be looking for, because when you're going in, you're trying to decide what test to do, and I'm going to do this in the grand scheme of like all AP possible questions. If you see a two-way table like this, and there's is there convincing evidence? Most likely chi-square immediately. That is somewhere where you need to be. It's either a test for independence or it's a test for homogeneity. Two-way table, is there convincing evidence? And then you kind of go in, you read the question, and you see the word association. As soon as you see association, that immediately is a test of independence. Nothing else matters at that point. Now, say for instance, okay, you saw it, but you're like, okay, I can't remember if association was homogeneity or if it was independence. The next thing I would kind of jump to is how did they collect their sample? And in this case, they took a SRS of 300 RHS students. Yes, eventually they sorted them into high, low, and middle GPAs, but they did not sample separately. So because we have a single sample, that is what also leads us to a test of independence. And then again, just looking at the question, we have two categorical variables. We have anger level and GPA with one population. So that again, another sign that this is a test of independence. The first thing I would be checking for if I were you is the word association. That's the big one. If it was a homogeneity, they would say, we sampled 100 low GPAs, 100 middle GPAs, 100 high GPAs to see if they are the same for anger level or to see if there's a difference in anger level for each of these groups. So if you see same or different, that is homogeneity. If you see association or independence, that is a test of independence. So the null is the dull one. We are going to go in and we are going to say anger level and GPA. The null is dull. No relationship between these two things, so I'm going to say are not associated. Within the hypothesis, you can specify your population. I'm going to go ahead and just do that in my conclusion just to save myself some writing. And then in my alternative, anger level and GPA are associated, because that would be more interesting, which is usually what the alternative hypothesis is in the case of chi-square. We have three conditions. Two of them you should be super, super comfortable with at this point. They are taking an SRS of 300 RHS students. And remember, you can only say SRS if it says SRS. SRS is a type of sampling, a type of random sampling, so they get real specific about you cannot just assume that that is how they did it unless they say it. And then the independence is the 10% condition, and here's where we're going to kind of say we think that there's 3,000. I can't remember the exact count of students in RHS at the current moment, but we're going to say it's safe to assume. It might be a little high, but depending on like how many freshmen there are this year, which is usually a lot, we'll say it's safe to assume. Now, for the third condition, that's where I kind of go in and I do a little backwards thinking, because I don't want to have to calculate all of the expected values. Remember, from your table, your two-way table, not including any rows that were totals, which we don't have any here, this is our observed data. So this matrix, this 3x3 matrix, is what I will be typing into my calculator. Now, I have to find expected values for every single one of these cells. And so in order to do that, I don't want to have to calculate them on my own, because I would have to take row total times column total over table total. So what I'm going to do instead is I'm going to put this data into my calculator and I'm going to run the test, and then I'm going to come back and I'm going to fill in expected values. If I were you, what I would do is I would either leave a blank or I would write an empty matrix so that you don't forget to come back, because that is one of the big mistakes that people make. They are like, yes, I'm going to keep going because I know I don't want to calculate those, but they don't go back and actually write them down. So let's go in. I'm going to name the test, and then I'm going to jump to my calculator. Chi-square test for independence. Now, what I'm going to do, let's see. There we go. It should be coming. You want to enter in your data into matrix A. I usually just use matrix A because it is the easiest one, because you don't have to change anything. You go to second X inverse, and it's the little button right underneath math. You should see the word matrix written above it. And then you're going to go to edit. And this is a 3-row, 3-column matrix. So I went ahead and typed in the observed values. Make sure that you are typing in observed data. Typically for these types of questions, they don't give you expected values, so you should be fine. But this is what we actually counted from their sample of 300 students. And then once your matrix is in, you're gonna go to Stat Tests C. So not the chi-squared goodness of fit, just the one that says chi-squared test. So I'm gonna go to Stat Tests all the way down to letter C. And then you really have no choices to make. You're making no decisions. You just go all the way down to calculate and you hit enter. This is what I would do if I were you. I would take these values, I'd write them down on my paper, because you're gonna need them either way. And then once you have this written down, you can go look at matrix B, and it should be populated with all of your expected values. So everything from the 3x3 matrix for expected values should be there. Don't worry about having to clear matrix B before you run the test. Your calculator is automatically gonna override anything that was previously there. So I'm gonna go in, I'm gonna write this down, and then I'm gonna go look at matrix B. So this was chi-squared 187.1097, P0, degree of freedom of 4. And then I will jump back to my calculator, and then I will go to second matrix. Now, here's just personal preference. I go back to edit, and then I just click on matrix B, because I can take my cursor and I can move around and I can see the full decimal for each cell. So sometimes in your calculator view, it doesn't give you the full decimal for some reason. It picks and chooses when it's gonna do the whole thing. So I can even see, like if this was 7.6 in my window, I can click on the cell and see that it's 7.52. I normally go about 2 decimal places just when I'm writing my expected values. There's no true rule. I think 2 is a safe bet. Oops, wrong number. This is 37.58, but you do have to write them down. 107. And then one of the questions I've gotten is, what do we do if one of them is not bigger than 5? If this were an FRQ, kind of like what I've said before, I would not stop the test. I would still go on. I would still interpret my p-value. Just in the conclusion, you would have something that says, however, the expected counts condition failed, so it may not be an accurate result. Best guess that I have, AP-wise, is they are not going to give you an FRQ where a condition is failing. Now, that's a big statement, but I don't think that that is their goal. They are not trying to have a gotcha moment where you were supposed to stop the test and you kept going, so we're not going to give you any points. That will not happen on an FRQ. If anything, conditions will fail when it comes to multiple choice. They may give you a situation, they may say check the conditions, and it's like kind of like what you guys do in math lab where it's like the random condition failed, so blah, blah, blah. But I don't think that that would happen in an FRQ. FRQs, most likely all of your conditions will always pass. In this case, they're all bigger than 5, so we say it's wonderful, it's great. We move on to our conclusion. Since the p-value of 0, which is very, very small, is less, and if you don't have an alpha, we assume 0.05. If you have less, we reject every single time. Now, with the reject, you're always going to have convincing evidence. And here is where I'll give a little more context to the specific population. I'm going to say that anger level and GPA, and this is specifically for RHS students. It did not sample from a larger population than RHS students. For RHS students are, let me make sure my grammar is correct. There is convincing evidence that anger level and GPA for RHS students are associated. And just, I'm thinking of all the possible multiple choice questions that could come from chi-squared, which is where it's usually most popular. If you were asked to calculate the degree of freedom, that's your number of rows minus 1 times your number of columns minus 1. So that's 3 minus 1, 3 minus 1, 2 times 2. Sometimes they don't give you a table. Sometimes they don't give you the data. They will say something like, there are 3 categories for anger level and there are 3 categories for GPA. What is the degree of freedom? It's still the same idea of a 3 by 3, 3 minus 1, 3 minus 1. So it's the number of categories for each variable multiplied together. I want you to try, just to get some practice on your own, try example 2, and then we will see if we get the same value in about 3 or 4 minutes. It's basically, and I'll zoom out just so you can see my whole setup. It is essentially, you're doing the same exact thing. I just want to make sure that you have practice with your calculator in putting in the matrix and running the test, because that is one of the things I get questions on during the test. How do I put a matrix in my calculator? I cannot answer that on test day. So give it a go, try it out, and then we will compare answers in like 3 or 4 minutes.